Hello everyone, welcome back to the Magpie project updates. This is week 2, so I guess it'll be part 2. And so we kind of did a general overview of Magpie, and if you didn't see that video, I'd recommend going and seeing that. Again, I do drone on for quite a while, so if you just want the basics, just go look at my GitHub below and you can read the README, and that is a kind of out-of-date version of the project, but as time goes on, it will be updated. So this week, I wanted to more talk about the science itself. So like, what are the probes actually doing? We know that they're landing on Mars. We know we have 6 of them. We have 2 redundant. Now, admittedly, because we have 2 redundant, I might be inclined to cut down on the number of probes. There's multiple reasons I would do this. Some would be fuel and design size. Down selecting the amount of fuel might make the mission cheaper, but that's a later video for that. Today we're going to be just talking about the science, the methods, and the site-specific goals. So first, the probe network, science, and how we measure it, how we have the identical probes and pull-to-pull coverage. And kind of with that, we'll have the time-synchronous meteorology, the electrification, and imaging all at the same time that all of the probes can do. Because they are, again, identical, they can kind of change their mission. So, again, that kind of goes back to the redundancy. We can kind of rank the order of importance of these probes. So, with the descent profiles and landed stations, because we will be recording data during the EDL section, or the entry, descent, and landing section of these probes. Okay. So, instrument suite, as of this moment, we've got way to measure pressure, temperature, relative humidity. Relative humidity will be referenced as RH. For the rest of this, we've got a CO2 detector. We have a solid-state thermal anemometer. And again, we don't want moving parts. We want to reduce that. And the solid-state thermal anemometer can also be very useful for wind speed of different directions. With a standard anemometer, you're going to have something rotating, or potentially you're going to have a fan rotating and you're holding it this way. But with this, it doesn't really matter which way the wind is direction. So like, let's say we actually have a test aeroshell here. So let's say this is the probe. Let's say this is the bottom of the probe and this is the top of the probe. Basically, what if the probe lands and it's like this, and our anemometer, let's say, is at the top? Well, it's still going to be able to measure that wind speed, but if it was mounted for the direction of going perpendicular to my hand, it means that it would measure only 45%, or it'd be offset by 45 degrees. So with the solid state, we don't have to worry about moving parts, and as long as we know the orientation of the probe, it makes it a lot easier and more accurate. So that's really beneficial. We have the electrification. This is just a broadband E-field antenna. It's basically an all-band. And it will have a preamp just to help pick up any signals. And the main reason for that is lightning detection. And with that, we can determine the distance of the lightning and potentially the strength of said lightning. So that would be really beneficial to have, especially if, let's say some of these probes live long enough to have a global dust storm. Maybe they don't survive for that long, but they survive long enough to be able to get a signal out and record this data. Of course, the data will also be logged on the probes themselves, so they can be transmitted at a later date. And I kind of will talk about it, but the system does kind of have an auto rank feature of events. It can kind of self-determine an event, and based on that, it will determine which is the most important data descent. And finally, acoustics on this section. We have more instruments than this, trust me. And we have a microphone for wind, dust impacts, microquakes, and other mechanical events because, for example, it will be activated during re-entry. I think that'll be very useful to know especially if, let's say, we do one probe at a time. That means we might be able to better position the reentry profile for the next probe if there is a significant level of strain, and part of that is going to be the noise that we collect. So navigation and descent profiling. We'll have a 6-axis IMU, which will be polling at 200 hertz, an altimeter. Right now, I'm not quite positive on which way I want to approach. Part of me actually wants to do a pitot tube because they're highly reliable, but it would mean an entire system of a little heater and things like that. I could go radar, and I might end up going radar, but we'll kind of see. And we could also use a simple barometric reading. But that's, again, all kind of in the works. And then a tri-axis magnetometer, which won't be that useful, but good to have. Our cameras, again, I talked about this last week. We'll have 3 cameras. I would say that the most important camera is the side still camera. I can record in color, but I do plan on having it actually transmit mostly in black and white. It's just lower bandwidth. That's the simple way. It'll be horizon looking, ideally, again, in that same situation of the probe looking down. Hopefully we'll be out horizontally. We'll kind of see. The way it'll be designed for landing is obviously to make it as smooth as possible, but we can't guarantee anything. It'll be able to do a single frame at an extended period of time, so we'll be able to hold the shutter open, or it can do a burst. I'm not sure exactly what that'd be useful for, but I know that during descent it will be. So that feature will be there. I'll look at nearby rock, regolith, and star tracking because it'll be another way to determine our altitude and our actual position of the spacecraft, or the probe, sorry. We'll have a bottom-facing descent camera. This will look through our landing system, and that'll also be in color. And this will give us a lot of different imagery. It'll give us nadir imagery during the entry, descent, and landing section of this mission. Yes, we have orbiters that have magnificent cameras like the NRO, but it's good to have more local footage live while recording. Yeah. We'll also have a side thermal camera. This will have the same view as the side still camera, also known as side cam. I'm not quite sure on my naming convention yet, so I'm sorry for the confusing parts of it. This will be pretty much an extremely low resolution image, truly like bare bones, like I'm talking like maybe 24 by 60 pixels. Very simple, very easy, but it'll give us a scene temperature and give us some contrast compared to our single point temperature. We'll actually have external temperature and internal temperature. That's merely for battery regulation and things like that to know inside. And then we might be able to determine cloud edges and dust fronts approaching. Could be useful. We'll see if the model turns out like that. Of course, all of this data is not very useful if we can't power the probe and transmit that data. So right now we have 4 lithium ion. I want to change to nickel metal hydride. Those are my favorites. I likely will in the end, even though the specific energy of them are far lower. They're much better in terms of cycle performance and temperature performance. Mostly that low temperature. That's what I really care about. And then we have the main mode that uses that main battery, that 86 watt hour battery, and it will survive if it dies from that battery because it'll go over to the survival battery. This is a backup battery with 18 watt hours right now, and it's a lithium iron sulfate battery. These are non-rechargeable batteries, but they hold very well and have basically near the highest energy capacity of a primary battery, which is a non-rechargeable battery. They're highly reliable, been used on other spacecraft missions. So, and this this battery will be most useful likely at the probes, or at the poles, not the probes. And then our main communication system will be done on UHF 433 megahertz, which seems like an odd one. But mostly it's because of my familiarity with it, and so I can design a radio system far better and more reliable and better shielded at that frequency. So, like, I could have picked 450, which I was thinking about, but I've settled on 433 because of its ease of use and my in-depth familiarity with it, as I'm well experienced with RF engineering. The RF power of that will be 3 watts of power, which doesn't sound like that much, and it isn't. But the probes will be able to communicate with both the orbiter and any backup. So, other Mars orbiters have software-defined radios, which means they can receive this. The packet transmission is up for what I need to decide for the UHF side. We have another UHF radio, which I'm just nicknaming Laura. Laura is a off-the-shelf system, really. It's not very good at high data rates, but it's good at low power and a decent range. And this will only be 1 watt. So it's far less power, but it's a redundancy. And the orbiter itself should be easily able to pick it up because it will have amps on it. Okay, 1 second. Got a seltzer. So the measurement method and cadence. Obviously, we'll be recording during descent. Our IMU will be recording with probably a radar altimeter. And then vertical density, temperature via dynamic pressure and profile inversion. We'll have our bottom camera recording mostly during key events. This will be because we'll want to have it transmit as it's going, because let's say the worst that happens and the retrograde rockets fail to burn. That's a real possibility. Or maybe it's upside down and it goes into the ground even more. It's hard to tell, but it's good to have that extra data, because if something goes wrong, it wouldn't be all a waste. The other thing about this, so we'll have it during the key events, so the parachute inflating, the back shell separation, so the aeroshell, and the pre-flare, which is the retrograde burn. We'll have be able to determine rough flow winds estimates near surface. I don't think it's going to be possible for most cases, but with light regolith, it might be possible. So, again, I'm not a scientist. I'm an engineer. And to me, I'm just trying to create a wide spectrum of available capabilities for these probes. So on the surface, ideally, we want a 14 sol mission. I know that all these probes won't survive for 14 sols, but I do believe confidently that at least 2 will. And that's an altitude thing, or a latitude thing. It's just merely, you can only get so much sun. That is it. That's as simple as it is. So with that, we'll be measuring the metrology core, which is the pressure, the temperature, the relative humidity, and CO2 levels. We'll do a 1 Hz burst. It's just a recording. For every 5 minutes. And every 15 minutes, we'll be doing a background recording. This is just like a transmit, whatever. Wind, obviously, and then electric field, acoustic, side color, stills, and thermal. I'm not going to really say too much about these, other than side color will be useful for looking more at storms and clouds, and frost detection might be far more useful. This was detected, I believe, on several probes, but I know definitely for sure on, I believe, Viking 2. So, calibration quality will be offset via pre-flight chamber curves. These will also be helped by extended continuous common filters. And then we'll also have in situ cross checks. This is just for stability during the nighttime because the nominal temperature is going to be negative 60 degrees for most of these probes. And, most electronics are mil standard rated, which is negative 40. That's 20 below. And I talked about the mean. So we're going to get colder than that. Things are going to fail. Things are going to go weird. And while we do have an onboard heating system, it's mostly just to compensate. It's not to heat it up. It's just to protect the batteries at the end of the day. So sensors will drift. And that's okay. As long as we'll be able to compensate that because we'll know both the internal and external temperatures. And then we'll be able to do camera radiometry. Basically just determining more factors. So data products, these will be pretty much like the actual output of the sensors. So we'll have time series descent profiles, do a lot of imagery, events, and derived maps. These will be time specific maps, but it could be more super local stuff. So I've kind of gone over in depth about what we're actually recording, how we're going to record it. I haven't talked about where these probes are going. That's kind of important, I would say, at least. So, probe 1, Olympus Mons. It is in the high altitude area that we want to land a probe. Obviously, it doesn't have to be exactly Olympus Mons. Olympus Mons is huge, by the way, so we should be able to hit it. But right now, I have a very large rough estimate of the re-entry profiles. From my current math, I'm estimating I have a diameter of about 1,000 kilometers for a controlled landing, which is not good. Just full stop is not great. But I think that's mostly due to a failure in my design of the control system, so that'll be improved. So, what are the goals of measuring at high altitude? We'll be able to see up, down, slope, flow, wave activity, and cloud macroclimates. And we'll be able to determine turbulence and hazard models for future aerial assets, basically helicopters, like Ingenuity. But the other thing is this includes the sister probes. This is very important because the first probe, it may not be this one, but whatever is the first probe is kind of a sacrifice in a way, just because we haven't tested the hardware. In the mission that did kind of inspire this, Deep Space 2, they had 2 probes. No, that's not why it's called Deep Space 2. But both of them failed. And we don't know why. The lander also failed, but that's a different thing. And how are we measuring these? The anemometer, our meteorology suite, will be determined side color, camera feed, and a thermal to determine more on the cloud edges and determine cloud optical thickness, because we'll also be able to do this at night due to the increased length of our shutter time and our star determination. We'll be able to see surface roughness and flow line streaks for wind orientation validation. This will be confirmed by, we'll know the orientation of the wind based on both this visual that we'll see and by our sensors. I don't think I'm going to talk too much about these data products for each one of these things because I just don't think it matters that much. It does. It's just I don't think it matters to say. So I'm gonna keep these a little short because we have quite a few probes. Hellas Planeta. Wow, did not say that right. So it's just a deep basin, and I think it is the best chance for a human landing candidate. It is a large basin. It has some of the thickest atmosphere on Mars. It could have ice. It's arguable based on some of the papers. But also you have latitude. And that would reduce our radiation environment in Mars. So very useful. And we'll be determining a lot of these things based on our sensors. So, Planum Boreum, which is the North Pole, very simple. CO2 is there. There could be water ice, but the North Pole is kind of actually less interesting than the South Pole. The poles in the amount of CO2 are a little bit, or roughly the same, but more skewed towards the South Pole. So, South Pole. Sorry, I'm kind of going through these fast. I feel like I just keep repeating myself, and all of these slides will be posted on my GitHub under the documentation and science section. So if you want to read those more or you have questions, please let me know. So South Pole is probably more interesting because there's a higher likelihood, well, we know that there's water ice. We don't know how much, but I'm sorry. With the water ice, it would allow for a more permanent settlement, a base there. And with that, we would be able to see more of the CO2 deposition and circulation into the atmosphere, the volatile cycle, and maybe hit some water ice. Excuse me. So we also have these extra probes. We've talked about 4 landing sites. Those are the main landing sites. But I have 2 kind of around the equatorial site to kind of get an average. The benefits of both of these are it's very solar rich and they would live, well, they would just live. They would likely live less long than any rover. Maybe more of a Sojourner type of situation of life. But we'll see. And these are redundant, but could be used to really focus anything that we discover. And these probes are all programmable on the go. So, on the go during the mission, we could completely change the mission profile for any one of the probes to switch them, or do the same one, or, let's say we discover a specific crater that we want to look more into. We can kind of banish a probe there. So, now trigger logic and event modes. I kind of talked about this a little bit. Basically to determine, like, let's say this is the event logs. So let's say we have a dust event that's due to a pressure dip and a rise in the electric field and acoustic and image burst, and we would see that from the thermal cam. Frost trigger, we would see a thermal contrast, and we would see some threshold. We have the gust trigger, which is just wind. Communication would then be kind of determined in that order. Not this literal order, but it would be ranking the events on which is more important per probe landing. We'll be able to determine everything on the probe itself. It won't have too much computing power. That's kind of in the air. It's mostly because I want to decide on a computer that will be redundant, no matter the amount of radiation that is in my scripts to determine that. because, we don't want the computer just to die of radiation. And only so many are actually rated. But of course, like I've said in last week's, I want to make an engineering model. I'm not going to buy $1,000 PowerPC PC 104, 102 form factor, one of those two. But we'll be able to do some filtering of all of the data collected, kind of what is important, what isn't important. And most of it will be the daily summary. So the pro button will basically just do a calculation, plus any additional event packets. And this, according to my calculations, will be about 1.5 megapixels per pass. That is not including images. Well, it is just the lowest resolution ones. I'm talking like 240p black and white, which are fine for most cases. So why does Magpie matter? Why should we do it? Well, it would be the first synchronous multi-latitude boundary layer dataset, which would allow for better forecasting on Mars. It's a very interesting meteorology situation on Mars. On Earth, we did it for thousands, I guess, years, really like 150 years before satellites. And we've always had ground measurements, We've had air measurements before we had satellites, being able to take imagery at multiple wavelengths. But with Mars, we have the orbiters. We have the satellites already. We actually need the ground stations now to help verify that more. And the other thing about this mission is it's scalable. Ultimately, at the end of the day, the only thing that matters is the probes and the aeroshells get to Mars. From there, they can determine everything else. So it could easily be a simplex class mission by NASA, which is like $55 million. And we would do just a ride share to Mars with one probe. That's okay with me. Or this could be a dedicated mission and you send all 6. Or maybe you're scaling it down. You do only 4. These mission is very scalable. And, you could even bring a probe on a future mission after this mission has been completed, because the engineering has already been done in the validation of the dataset. It would also be able to help verify landing site safety. This is very important for both any payload and humans. It would kind of help with resource collection of data, and it validates the climate and EDL models. We've kind of already done that a lot, but it doesn't hurt for more data at different latitudes. And most importantly, I believe that with the collection of more data, especially near a human landing site, it de-risks human missions. Anything to de-risk a human mission, I think, is worth it. So with that, we're all done with the slideshow. So hopefully I didn't bore you guys too much. That was a lot of talking. So let's go see something more visually unique. Hello, everyone. So I've kind of droned on more with talking. So we're going to do something else. Get a little bit more of a visual aid of actually where our probes are landing. So we got Google Earth Pro here. I love Google Earth Pro. It is truly magnificent in its capabilities. So we have Mars loaded up here. This is just built in, no modification. And I believe we have the Viking map on, because I think it's the best looking. Yeah, we got Viking color on. I haven't loaded this in a while, so I'm surprised I remembered. So there's a lot of different sites that we can go. But of course, let's talk about the 4 main probe locations. So first, we'll talk about the North Pole. So as you can see here, there's quite a bit of dry ice. Again, there is some water ice, but it is far more impactful of the actual CO2 ice here. And for reference, I want to get a probe within the actual diameter of the ice cap. It's not going to be amazing because right now we are looking at autumn for Mars, for the North Pole. So that means it'll be spring down here at the South Pole. And actually you can see this great variance of the winters here. So it actually looks to me like this is maybe midwinter here and midsummer here even. Or maybe early winter, midsummer, or early summer. Sorry. So we can see that there's the huge difference, but this amount of CO2 will go to either pole depending on the season. And so you have kind of this this area that stays perpetually under dry ice in the south here. And that's where that water is always frozen because, of course, to get dry ice, it's always sublimating. Whenever you have it nearby, that's why people use it for the experiments and stuff. So it needs to be frozen at a much lower temperature. So those are the two poles of landing. And then let's look at Olympus Mons, which is right here. This is Olympus Mons. Huge mountain. Look at that compared to the diameter of Mars. It's eyeballing it maybe 1/15 of the size. And here we have a chain of mountains that I'm blanking on them. Now these are actually all in the highlands, and pretty much opposite is this lowlands of Mars. Now of course we're looking at color imagery, so it's kind of hard to tell radar. So let us do colorized terrain. And so as you can see, the blue is the lower elevations. So you can see that at that point I just elevated is pretty low. And then we have this. And this is, well, let me verify, yeah. So this is Hellas Planeta. Plana. I'm still enunciating it, sorry, incorrectly. So this is the general target site for my probes, and this is where I believe that the future landing sites of humans will be. I think there's a very real possibility. Yes, I'm aware of how cratered everything is, but this is where the atmosphere is the thickest and you have the most layers of protection. And look at this erosion. This has to be water, if I remember correctly. So, super fascinating geology. Planetary geology is fascinating. And let's go back to these highlands. So we've got these nice mountains here, but there's Olympus Mons. You can see it's in white. It is that high in elevation, and so is this chain. So merely getting to, not necessarily like on the mountain, is a priority, but I think an elevated place would be really amazing. So I would love, somewhere around here, because this is a great big area of elevated area. Now, of course, you've got the Great Canyon here that I'm also blanking on the name. This is many, many, many times the Grand Canyon size, even especially by volume. So those are some of the landing sites on Mars that we're looking at, and we're going to refine it, but it's good to know. And here you get to see kind of the dual planet elevation. So you've got this massive amount of lowlands that takes up, well, let's zoom out to try and get a proper 50% grade, because your focal length matters in this. I would say really you could get like roughly half a hemisphere here of low terrain, with the exception of this mountain. And look at that. it's almost the opposite. There's very little blue. So with that, I'm gonna actually just take my hands off and talk about some of the updates that I've been working on. So I currently have 2 generations of Aeroshell. Neither are going to be the final. I have identified problems with both of them. I'm unhappy, but that's okay. I like iterative design. So I've already showed this, and this is Gen 1 Aeroshell. It is a 70-degree nose. It's not amazing, and it's got a rough diameter of just under a meter. And it is theoretically aerodynamically stable. As you can see, it's actually got quite a bit of height, and this we have just one single plane here. Now, Gen 2 was to more closely model, so this was to approximate Pathfinder's reentry, and this was to more approximate Mars Science Lab. Now, I'm not sure how well you can see here, but we've actually got 2 graduated segments. So these are at different plane angles. And then we've got a more blunt reentry side, and it's actually deeper. And so these are in the same scale. So you can see that total volume is actually Gen 1 has the advantage there. And so one of the things that I'm working on, I'll kind of add on in this update section, is my propulsion system for reentry, before EDO. And I have kind of thought about adding essentially a booster structure on the outside of this ring here, very similar to the Mars Science Lab. But recently, and that would be a hydrazine mix. And for the mass of these probes, you need less than 2 kilograms of hydrazine to do so. That would be, math in my head, about 2.5, 2.4 kilograms of total fuel plus propellant, which is not bad with a lot of redundancy. Of course, redundancy means extra weight, extra hazards, so we'd probably likely vent that during reentry. That's the thing. We have several ways to control this during reentry. We can have it aerodynamically stable, so we have the center of gravity, above the center of pressure, and we can control it from there a lot easier. Reaction wheels are totally feasible with this. In fact, I already plan on having them. Just full stop. I want to have reaction wheels because it'll be very useful for changing from retrograde burn to our nominal reentry, because it's going to have a thruster going out this way no matter what, before or after the separations. The question is, do we want the reaction wheels inside? Which I think we do. We can have smaller ones that are less impactful. And the other question is, do I want to, instead of using the higher ISP and low boil off of hydrazine and compare it to a cold gas thruster? Cold gas thrusters are a whole different ballgame of propulsion. They offer a very terrible ISP. And ISP is essentially the rating of the energy released that you can get out of any propellant, I guess would be the term, and it's your specific energy. And so the higher the specific energy, the more energetic and more velocity and mass you can throw, which is propulsion. So with cold gas, it's not very efficient, and the pressure, the thrust depends on the level of pressure. Okay. Well, the other thing about them is they're dead simple. It is a cold gas thruster. There is no ignition. It is just releasing propellant. Simple. The other thing is they're small. They're about this big for a very small one that would do plenty of energy. And they would weigh 10 grams each. I could have 4 thrusters, let's say one gets clogged up. That means you just cancel the one on the other side. It's very similar to the Saturn V first stage. So these are very much options, and these are things I plan on investigating more in this coming week, alongside my general orbiter script for simulating our entire flight profile. Because as of this moment, it looks like I might be able to do the mission with all 6 probes on a Falcon 9 fully disposable, which would be a lot of money change compared to a Falcon Heavy. So I think it's definitely something I need to look more into. And with that, I don't think I have anything else. So thank you very much for watching. I know this one has been a long video, but I appreciate it so much. Thank you all for watching. Have a good week.